Okay. Is there something there? Okay. Control for this device. PC. Okay. One up. Okay. Suppose I say screen. Now let's hope our sound works. We'll find out in a moment. So, how you all doing this evening? This is the last leg of the journey today. After that, it's beer 30. Okay, everybody is here as a math and music scholar as of right now. So, good to have you here. Thanks for grading a course called Mathematics and Music. This will be a quick run through. It's only an hour, so won't go over a bit. I did a 2-hour version earlier today, so I may zip past some things that we belabored a little bit more in the 2-hour version. But you might actually be thankful for that. But what I want to do is just talk a little bit about connections between mathematics and music. It's not so much as how do you use music to do math or math to do music. It's the synergy between the two subjects, and it's something that's dear to my heart because I'm a mathematician in real life and a musician just, in my avocation. So, but I'm very much involved with both, and I teach a course in mathematics and music at my university, which is Washington University in St. Louis. So, now let's see if my gizmo works. Yes. This is a little book I wrote. You can find it on Amazon.com. It's probably the easiest book ever written because I had the course notes to this class that I teach at the university online, and one day in walks the guy who was the editor of the American Math Society publication wing, and he said, "We'd like to take your course notes and make them into a book." I said, "All right." They paid me and everything. So it was a little more work than I thought. I had to kind of revamp the notes a little bit. Had to make references and all that. But basically, it just describes what I talk about in whole semester at the university, which is all these notions of math and music that interrelate. So the story of music and math relating and interacting with each other and also attracting the same people's interests is an old story. For example, Pythagoras is well known in musical circles and well known in mathematical circles. One of the great classic theorems of mathematics is the Pythagorean theorem, which relates the hypotenuse of a triangle with the sides. And Pythagoras was also interested in music, and in particular in tonal relationships. He was interested in why certain tones sound good when sounded together. And so he realized that there were mathematical relationships between those frequencies. And he wrote that down. And then he also tried to get the scale to work out. He realized it didn't quite work out. And so that, after many centuries, ended up with our system of equal temperament, which harkens to this guy here, Johann Sebastian Bach, who was primarily a musician, but was also very interested in the mathematical problem of how to tune up the scale. It turns out you can't really tune up the scale so it's in tune. At the time of Bach, scales were tuned asymmetrically, so keyboard instruments, the intervals between all the semitones weren't the same. And therefore, some keys had a different sound from other keys. And the tonic chord in the key of C sounded great. The tonic chord in the key of F sharp sounded pretty horrible. And so musicians learned to just abide by that and not use the dissonant chords. But of course, Bach was a great musician. He loved to modulate around. And one of his treatises is the Well-Tempered Clavier, which is nothing other than 24 short pieces, motets, that represent all 12 of the major keys and all 12 of the minor keys. And And the purpose of that was to demonstrate that they all sound equally good, or if you want to look at it that way, equally bad. The scale is tuned up equally. They all sound the same. It doesn't matter what key you're in. I ran across this fantastic quote. I'm going to just let you read it. This is Rabindranath Tagore. He was a Nobel Prize winner, and the first non-European one. And I was in Calcutta giving talks at the India Institute of Statistics, and I just saw this quotation hanging on the wall of their library, and I thought, man, that is amazing. In his flowery way, he was saying basically that the synergy between mathematics and music is really at the heart of all creation. And so Tagore and many other poets, scientists have really appreciated the relationship between music and mathematics. So there's some concepts you can read about. You learned about all these concepts at some point in your early mathematical courses in grade school and high school. Trigonometry, for example, studies right triangles, but it also studies function theory, such as y equals sine of x is the most basic trigonometric function. It has a graph that's a curve that you all can visualize. We'll talk about that later. But integers are the counting numbers. Rational numbers, those that can be written as fractions of counting numbers, like 5/3. Real numbers are all the continuum of the real number line, so that includes things that are not fractions, like the square root of 2 and pi. And so all of these things are involved in music. Musical concepts that relate to math, well, obviously tempo and rhythm, that's counting. Scales and key signatures, melody and the form of melody and the form of music in general. Pitch, intervals, tuning, tone, timbre, all of that is mathematical when you come to really analyze it. So I'm going to give you the fast forward version. By the way, even though I may be going quickly over some things, please stop and ask if I race past something you want to belabor for a while. I'm happy to do that. So please, please, please contribute if you wish.
Can I ask, how did Pythagoras know about frequencies? How could he measure them at that time?
So he had figured out, how did he actually know what the frequencies were?
Yes.
I'm not sure he knew what they were so much as he knew the relationships between them. So he had figured out, for example, if you take a string and pluck it, and now you take the same string and make a note halfway between, it was an octave above. So he realized that the distance, if you have the distance, you double the frequency.
And the two sound good together.
Yeah, and the two sound good together. And he studied nodes, you pluck a string and it forms nodes and blah, blah, blah. So it was basically integer relationships between frequencies. So no, he probably didn't know what A440 is, something like that. How do you measure 440? Yeah. Okay. The basic temporal notation is very suggestive of all of music and the way it relates to mathematics. And the reason is because its powers are 2. And that goes back to the fact that our brain likes simple concepts. And 2 is a simple concept. Basically, if you take a rhythmic pattern, everybody clap along with me. Okay, stop. Now do the same thing, but double the frequency. Okay, now double that. Ready? And now you may not have physically been able to do that, but mentally you can do it. So that's all that's happening right here in our sequence of notes. Each one halves the duration of the one before. So if you have it in sequence, you're doubling the frequency or halving the duration. And so our notes are indexed by powers of 2. 1/2, 1/4, 1/8. 1/16 to 32nd, 64th. Those are the reciprocals of the powers of 2. And all that is suggestive of the fact that you can take a temporal interval and halve it. And that's something your brain processes pretty well. You could probably do pretty good at dividing it into thirds. But if I asked you to divide it into 7 units, you would struggle with that. And so would I. Because our brain just doesn't think that way. So we like small integers, like 2. That's a real small one. Yeah?
Is that true of all world music or just Western music?
It's really true of just about every kind of music, and we'll see the powers of 2 coming into not just the temporal or horizontal structure, but the vertical structure as well. But yes, I mean, that's human beings,
these are concepts that didn't have to be invented. The basic concepts of mathematics are just universal. If we encountered somebody from a different galaxy, our notion of chemistry and a lot of physics, and certainly biology, would not be applicable to them. But the notion of mathematics, like the notion of 2, that's universal. And when I say universal, I mean universal. And the notions of music are too, because they talk about intervals of time and division, and they talk about rates of vibration. So something happened at a rate of vibration, that's pitch. Those are universal too. So mathematics and music are two things you could speak with somebody from a foreign galaxy whose organisms are totally different. Biology would make no sense. Our history makes no sense. Our chemistry makes no sense, perhaps. But our math and our music, that makes sense. Now that's why I like those two subjects. So here we go. This is just universal stuff we divide by 2. All right. Now, there's even a quirk in this with our dotting notes. And I noted this a long time, and I even, ages ago before I really got serious about thinking about math and music. When you dot a note, what are you doing to its duration? Yeah, you're adding 50%. So if the duration of the original note was D, so let's write mathematically. The dotted note has duration 3/2 times D, 1.5 times D, or D times 1 plus a half. And if you put 2 dots, now what are you adding to it? Well, you're adding half again, or 1/4 of the original. So it's the original thing times 1 plus a half plus a fourth. You rarely see it, but you could have 3 dots, and that's the original duration times 1 plus a half plus a fourth. So what are you adding here when you're adding consecutive reciprocals of powers of 2? It's the same thing as the temporal thing we talked about. In other words, you're just adding the next note on that sequence and tying it together. And here's the thing that every mathematician sees this and realizes, this is what's called the geometric sequence. If you add up infinitely, now you may say that makes no sense to add infinitely many fractions. But as a matter of fact, in mathematics it does, because we take a limit. The limit of the sum, 1 plus a half plus a fourth plus a 8 plus a 16th plus a 32nd plus a 64th plus 1 over 128, etc. forever, it all adds up to 2. I think I can convince you of that if you don't already see why. Let's suppose the distance between this end of the table and that end of the table was 2 units. All right? I'm going to walk 1 unit. That's right here. Agreed? Now I'm going to add a half. I'm going to walk half the unit. So now I'm right here. Now I'm going to walk 1/4 of the unit. Now I'm right here. Now 1/8. Each time I'm going halfway the distance between where I am and the destination. Now, you say, well, you can't add all those up. You can't. But in the limit, you get 2. All right? So what does that say musically? The infinitely dotted note is just the next note up. You can never exceed the value of the next note. And it's amazing that musicians came up with that notation that harkens to the geometric series that every mathematician is quite familiar with. Let's talk about meter. Meter is given by a pair of integers. Integers are the whole counting number, positive integers. M over N. The bottom one is always a power of 2. You'll never see a meter that's where the bottom integer is 7. It's always 2, 4, 8. It could be 16. In principle, it's a power of 2. Because why? Well, the top number can be anything. It tells you what? What does the top number say in time signature? Yes. How many beats there are in our unit of our temporal unit, which is a measure. So it's how many beats there are. And the bottom note indicates what? Okay, it harkens to those notes on that list, and it says it's picking out that power of 2 for the note that's going to be 1 beat. Okay, so the 3 over 2 says there's 3 beats to the measure, and the half note gets 1 beat. 2 over 4 says there's 2 beats to the measure, and the quarter note gets 1 beat, and so those two integers have that significance. All right. Now, almost always, the numbers aren't very big. You don't see a time signature of 19 over 32, although it is possible. But we like to think in small numbers. Our favorite number is 2. We like to count in 2s. So here's some audio examples now. Let me open my... Yeah. So here it is 1 and 2, 1 and 2. Typical duo rhythm. You count in 1 and 2 and 1 and 2. And that's the way you go. Right? So it's in 2s. Less common, but very common, is in 3s. And that would be many, many songs, but soft shoe kinds of songs, but classically waltzes like this one. This is a bit not in perfect rhythm, but you hear the threes. 2, 3, 1, 2, 3, 1, 2, 3. And you're basically feeling that 3/4 tempo, which means that it's probably written with quarter note in 1 beat, but 3 units that we're counting off. 5s or 7 and 7s are less common, but they do appear. Here's an example where we count in 5s. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. And even though it's a little non-standard, it's a great sound. And part of the intrigue of that is that it is counting in 5s. In fact, what's the name of that composition? Name 5. It's so unusual that it's named after its time signature. 7s and any number bigger is highly unusual, but here's this counting in 7s. I remember when I first heard that song, I thought, hoodwinked. It's like, oh, something's missing there. But that's part of the charm of the song again. It's the incompleteness. 7 is close enough to 8 that you're expecting that extra beat, but it doesn't happen. Now, if you listen to the longer passage of the song, you realize that eventually it does slip into 8s, which is another great thing about music. It sets up kind of this incomplete feeling and then eventually fulfills your expectations. So that's kind of a neat game that composers play in various ways. So basically the idea is that we like to count with small numbers. We like units, small groups. When you get up to 7 and 5, it's already a little bit non-standard. All right. Now, we can spend a lot of time talking about form, but in mathematics, sometime in high school, you drew the graph of y equals f of x. If f of x was x squared, you get a parabola, for example. Y equals x squared. You draw the graph. And then you say to the 6th grade student, okay, here's y equals x squared, here's the graph. Suppose I say y equals x squared plus 2. What's the graph? And the student does a view, and they, oh, we just shove everything up by 2 units. All right? And if we say, what's the graph of y equals x minus 2 squared, quantity squared, and that moves it over. Yeah? So we've got these horizontal and vertical shifts, which is a math concept and a music concept. So first of all, music repeats. Here's O Christmas Tree or O Tannenbaum. The first repeating thing you notice is that it goes bum bum ba-dum bum bum ba-dum bum or bum bum ba-dum 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 bum bum. So these two measures right here are the same rhythmically. We're just thinking rhythmic. They're the same. So it's what you might call a horizontal translation. It's just taking the same thing and repeating it. And as a matter of fact, the song doesn't do exactly what it says. It does this whole thing, then it does this again, and then it does that, then it goes back and does the first thing again. So you've got this repeating section where everything is just like translating it over to the unit by 4 bars. But not only that, but in this one section that's different, you notice that the notes in this group kind of resemble the sequence of notes in this group. In what way? Well, in the way that if you just take everything and shove it down a line or a space, with these, you get those. All right? Yeah. So that's what we might call diatonic, to use a fancy word, translation. It just shoves everything down by a scale tone. So, well, you all know what that sounds like, but I'll play you my sound bite here, where the piano player doesn't quite play it exactly the way it's supposed to be. So the first thing is that this repeats, goes back here. here's this business with the translation. And there's the same thing again, the down and the stylization. And then it goes back there and does that again. Now, we can talk about the overall form of that in music. We would call that form AAB. Does that make sense? You did something, you did it again, you do a B section, we sometimes call it a bridge or just a contrasting section, and you go back. It's the most standard thing in all kinds of music, pop music, classical music, everything. But then within the B section, you have this nice little symmetry, which is just a strain, and then the same thing down 1 unit in terms of scale tones. Now, here's another example. This is called chromatic translation, and I'll distinguish the difference or let you observe the difference. This is Gershwin's Strike Up the Band. And if you look at this melody here, we go down to here, to that point, right there, it really does the same thing it did back there. It does the exact same thing again, except you might say in a different key. The starting point here was F, the starting point here is B flat. But other than that, it does the same thing. It just repeats the same thing. So you can hear that happening. Up here shoved everything down by a scale tone. This one shoved it up upward, and by how far? So it's here to start on F, and there it starts on B flat. So music theory people, what's that interval? It's a fourth. It shoves it up a fourth. Now, what else is different about these two kinds of translations? One I've used diatonic and one I've used chromatic. What's the difference? How are they fundamentally different?
Chromatic isn't part of the key signature.
Pardon me?
Chromatic is not part of the key signature.
Okay, it gets out of the key signature, it gets out of the diatonic scale, gets out of the scale if it has to. But actually, let's go back up here. Was this actually a perfect transposition? Yeah.
It's very close. It's
close.
It goes down. Everything's gone down the note in the scale.
In the scale.
Whereas everything in the bottom one has gone up by exactly the same.
That's, man, way to go. Okay, so this is an exact translation. This one goes down a half there, this one goes down a half there. This one goes up a minor third there, that one goes up a minor third there. So there are accidentals, actually there's accidentals in the original, and there are accidentals in the second one, but the second one may require accidentals that the first one didn't require, or maybe doesn't have to have accidentals that the first one did, whatever, to make it happen exactly the same, but starting in a different place. This is diatonic, which means, as you said, it preserves the scale tones, but scale tones are not all the same, right? In our major scale, there are a bunch of steps, and there are a couple of half steps. So if you shove everything down to scale tone, you may not have the same interval. For example, this is from C to B flat. That's a step right there, but its shoved down version is B flat to A. That's only a half step. So it doesn't preserve the intervals exactly. It preserves them diatonically. But both are very legitimate things in music. If you start looking at symmetries in music, not only do you see the overall form of things, but internally within phrases, you see these geometric transformations all over the place, where the same thing happens again, but differently, because it's maybe a diatonic translation or a chromatic translation. And that's part of what makes a lot of music interesting, of course. Start studying music, you see all kinds of symmetries. Okay, let me talk a minute about modular arithmetic. Now, mathematics is equipped to model two kinds of phenomenon. So one phenomenon is something goes on forever. Like if we draw an x-axis, you know, like you did in high school math. In the positive direction, positive direction it goes on forever, and the negative direction goes on forever. So that's like if I take off through the universe, and go in a straight line, presumably it goes on forever. Another thing is you follow the curvature of the Earth, and it seems like you're going straight, but you're really not, and you come back and you end up where you start. So I can think of counting in such a way that instead of going along a straight line, I'm going in a circle, and after so many steps, I'm back to 0. Right? So that's a modular notion. That means after so many steps, you're back where you started. We encounter that in music a lot. If you think about going up in half steps, we think octave equivalent. So if I go C, D flat, D, E flat, E, blah, 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 the 12th step, I'm back to C again. And we say that's the same note. It's not the same note, but it is in music. We say C or E flat. We don't distinguish between octaves. So music has many, many phenomena that use modularity, which means you take Z, by the way, is our, in symbol math, that blackboard Z for the integers, after the German word Zeichen, to count, counting. So when I put the subscript in, that means that starting with 0, I put brackets around these to indicate they're modular. I get up to n minus 1, and then the next one, instead of being n, it goes back to 0. So just think of counting in that circular way, as if you're taking steps around a circle, and after n steps, you're back to 0. Okay. Now, that relates to music in many ways, believe it or not. Here's the first one. And this is, I probably should have started with a simpler one, but here's the most striking. Now, let's suppose I have two different positive integers. I'm going to call them m and n. First thing I want to introduce you to is the notion of the greatest common divisor. That's a pretty obvious concept. If I say 12 and 9, what's the greatest common divisor? It's 3. If I say 6 and 4, what's the greatest common divisor? 2. All right. If I say 21 and 14, what's the greatest common divisor? 7. You got it. So that's the greatest common divisor. Now we say two integers are relatively prime if their greatest common divisor is 1. So for example, 12 and 9, 12 and 8 have greatest common divisor 1. Oh, excuse me, 12 and 7.
You're a professor and you're allowed to do that.
I was just checking to see if you were okay. All right, now, many composers write passages where you've got M notes, or Bs, against a pattern of N such, where the greatest common divisor is 1. And it exploits, perhaps unknowingly by the composer, the fact that M, if you have this phenomenon, greatest common divisor, M is what's called a generator in this system Zn, and by symmetry, N is a generator in Zm. Now let me explain what I mean by that. I want to choose two integers that are relatively prime, and give you an example. So I'm going to choose 5 and 3. All right? Now let's think about the fact that they're relatively prime says that 3 is a generator in Z5. Now Z5 is that system where I count 0, 1, 2, 3, 4, 0. Okay? And let's think about adding 3's. And what I'm going to claim is that I get every modular integer before I get to 0. So we start at 0. Now we're in Z5, so our circle has 5 steps. And we take 3 steps, so we're at 3. Now I take 3 more, so that's the 6th step, but that is 1. I take 3 more, 4. I take 3 more, 2. And I take 3 more, 0. I've hit every modular number. Yeah? It works the other way around. Let's take a modular system of 3. So Z3, 1, 2, 0. Let's start adding 5. So the first 5 lands me at 2. And add 5, 1. And add 5, 0. Got it? Now, about 3 of you are looking at me like you're ready for your beer right now. You get the idea. Okay, now you think that's just a funny little exercise. First of all, it's not perfectly obvious that if M is a generator mod N, that N would be a generator mod M. It's not obvious at all. But it happens exactly when the two are relatively prime, and that obviously is a symmetric property. So there's one of the marvels of mathematics. Sometimes two things that don't seem symmetric are related to some concept that's obviously symmetric. You realize, oh, if you generate one on the other, then the vice versa thing has to be true as well.
Does the same apply for 4 and 2?
Not relatively prime.
No, relatively prime, so it's
4 and 3?
4 and 3,
4
yes.
and 5?
Yeah.
Test it out.
Yeah.
Find 2. You take 14 and 19. It takes a while to verify it. You'll have a good time. Okay. Now, here, 3 and 4 are relatively prime. Now look at this little rhythmic figure. It comes in fours. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. How many pitches are there here? Well, it cycles through a pattern of 3 pitches. So I can think of this, let's think of the pitch as being modular, 1, 2, and 0. So we're mod 3, 1, 2, 0. We add 4s. So 1, 4 gives us a 1, another 4 gives us a 2, another 4, that gives us back to 0. Or let's think of adding 3s mod 4. So we start adding 3s, you're at 3, another 3, you're at 2, another 3, you're at 1, another 3, you're at 4, which is 0. And that little rhythmic and melodic figure works. Why? Because 3 and 4 are relatively prime. It also gives a very catchy melody. All right? There's some reason why this song called "In the Mood" was played by generations, and you start listening to it and you can't stop. And that's because of the catchiness due to that little phenomenon right there. So, and count the note 2, 3, 2, 3, 1, 2, 3, 1, 2, 3, or 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. You count by melody note, by position of the rhythmic figure. But it all comes out to the fact that you got a pattern of 3 against a pattern of 4, and therefore it takes a pattern of 3 times 4, 12, to complete the cycle. And it keeps doing that over and over and over again. So there's an example. Here's another more graphic one. This is a pattern of 5 notes. 1, 2, 3, 4, 5. Ba-da-da-ba-ba. Ba-da-da-ba-ba. 5 notes, 3 pitches. We're in the key of, whatever that is. What's that? E. So we have a D sharp there from the key signature. D sharp, D natural, and C sharp. And they just keep repeating. So you've got a pattern of 3 pitches against a rhythmic figure of 5 notes. So 3 is a generator mod 5, 5 is a generator mod 3, and you can play the same game. Add 3's mod 5, you get 3, 1, 4, 2, 0. And that completes the cycle after 15 notes. Yep. So it works because of the modular property. So everybody, I think, knows this passage, and you probably marveled at it many times, but maybe didn't realize why it sounds so cool. Does it again. And then, of course, Gershwin does the whole thing again, but on a different sequence of notes. Now it starts on F sharp. Okay, so now that has all kinds of symmetry. First of all, you have chromatic transposition, right? Because it's the same thing, up. You have this 3 on 5 game, which works because 3 and 5 are relatively prime. So there's really all kinds of mathematical concepts in that whole thing. Okay?
What about putting on the ribs?
So,
Kind of like that.
it's kind of,
Same phrase repeated with a different down.
yes. Yeah. Yes, what it has is kind of a passive bump, 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 ba-dum, ba-dum, the phrase takes 1 beat longer than what it should, and so you have this delay effect. Yeah, that's right. So it probably is the same thing. Absolutely.
So are you saying that George Gershwin and Glenn Miller had this innate sense of musicianship?
Yeah, I'm sure they didn't say, let's see, let me think of 2 small numbers that
about
don't.
theory and modular arithmetic today, let's face it. So
I won't say that they didn't, because I don't know, maybe they did, but probably
the
not.
mathematicians listened to it and thought, there's some maths going
Yeah.
on here.
Right. Yeah, how many notes? Well, it comes out even at the end of 15 notes and it starts over. Yeah, sure. I never want to say a composer didn't understand that, but it's quite likely that the answer is no. It probably just appeared in somebody's head one day. Sure. Here's another quick example of it. This is the Ain't No Sunshine. Here you're kind of going along in 16th notes. And now it comes in threes. So 3 and 16 are relative time. So it's up, 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 and ba, ba, da, ba, da, ba, da, ba, da, ba, da, ba, da. And this happens in a little vamp right in the middle of the song. This is one of my favorite songs from the blues. So it's got you carrying along with those, powers of two. Meanwhile, that backbeat is still in the, and then after a while, marvelous, marvelous passage. Okay, let's talk about pitch. Let's see now, what's my time? What time did we start here?
Just keep the, go right. We'll bring the berry. We'll bring the berry.
Okay. What do you mean by pitch? Well, our usual way of measuring it is in terms of cycles per second, vibrations per second. So the A, natural above middle C, the A that's kind of middle of the soprano range, is like 440 cycles. That's standard piano tuning. So cycles per second are called hertz after a German physicist. The range of human audibility is roughly 20 hertz up to 20,000 hertz. 20 is real slow. And actually, I always tell this story. This is one of the first math problems I ever encountered was when I was a little kid and had a bicycle. And we used to take you don't have baseball cards. Yeah, okay. So I have a card, and I always take a baseball card of somebody from a team that I didn't like very much, so that I could. And then I took my mom's clothespin, and I put it on the back of my bicycle so that it slapped against the spokes, and I took off and I had a motorcycle, right? So you take off, and I felt like I'm a big guy, you know? But I also noticed that when I take off, I could hear like slap, 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 and then it goes into what I detected as a tone. In other words, at some point, I stopped hearing individual hits, and I started hearing a very low pitch. And I tried to get on that threshold when I rode my bike, you know, like, okay, I can hear the slap, oh, I can't hear him, slow down, speed up, speed up. And then the first math problem I did, and I had a speedometer on that bike. So I figured out how many slaps per second is it when it stops being individual slaps and starts being a tone. So I had to measure the circumference of the wheel, how many spokes there were, what distance. I had to convert miles per hour on my speedometer into slaps per second. I was probably 7 or something. And I remember coming to the answer. It was something like 22, which is kind of roughly what that says. So about 20, you start hearing a pitch. And up around 20,000, it goes out of zone. And if you're older, like some of us in the room, it may be lower than that. Young people, a little higher. Your dog can go up to 40,000 or so. So anyway, you got all these pitches, and in principle, it could be, a frequency could be any positive real number. Negative doesn't make any sense in this concept. But it's parameterized by the positive real numbers. I write with a blackboard R, that's the real numbers. So not necessarily rational, but all real numbers. And the plus indicates positive. Any positive real number can be viewed as a frequency. So it may be out of the human audibility range, but it's still a frequency. Now, on a keyboard, we've got discrete pitches. So you've got C, B flat, D, E flat, E. Those can be parameterized by integers. Even on an infinite keyboard, that way infinitely high and infinitely low, those are discrete. So the integer, this set of pitches sits inside the set of all pitches, sort of like the integer sits inside the real numbers. It's discrete, even though both can be viewed as infinite. There's different degrees of infinity when we're in some mathematics. The integers is an infinite set, and so are the real numbers, but there's more real numbers than there are integers, even though they're both infinite. I won't go into that. It's going to ruin your evening entirely. Okay. Now, many forms of music exploit the continuity of pitch, not being forced into the discrete set of pitches that are on a keyboard. And of course, one of those forms of music is a cappella music, in particular barbershop, because we like to tune things, for example, differently from the way you would tune on the keyboard, for reasons that if I get there, we'll see. And also, we like to scoot continuously from one note to another. You can't do that on a keyboard. So let me play you a couple of other kinds of examples. This is an Indian rocker. You know, the sitar player. So the whole interest in the music is in the pitch bend. That's the whole skill of that melody player, to make the music mesmerizing by varying pitch continuously, not using a discrete. Here's another graphic example from Western music, probably the greatest music in history. So what would that be without the continuity of pitch? You have to have that for the clarinet to make that portamento. Of course, it requires a huge amount of skill on the part of the instrumentalist, but to take a reed instrument, you can bend the pitch. And a piece of music depends on the ability to do that. Okay, so we have pitch as a continuum. We can also talk about musical intervals in terms of the ratio of the pitches. So for example, here appears our favorite number 2 again. Probably the most basic interval in music is the octave. But what is the octave? It's double frequency. So if we start A440 and we go up an octave, we're at what frequency? 880. And if we go down an octave from 440, we're 220. So you notice that you can't measure the interval by the difference between the two. Because the difference between 220 and 440 is not the difference between 440 and 880. It's not the difference, it's the ratio. So when thinking of pitch as in terms of frequency, intervals become multiplicative, not additive. That's important, because when we think of them in terms of semitones on a piano, it's additive. If I take a major third, follow it by a minor third, so that's like 4 semitones plus 3 semitones, I would add semitones. I would get 7. That's a fifth. But if I take the interval of 2 to 1, followed by the interval of 3 to 1, I don't add a multiple. I get the ratio of 6 to 1. Right? So we have to think that there's 2 different ways of measuring intervals. One is ratio of pitch, and the other is this additive thing that we have on the keyboard where we measure in terms of semitones. Okay, so the ratio is 2 to 1. Now, our brain makes octave equivalents, believe it or not. There's a really good reason why, that I could talk about or not. But when you hear notes an octave apart, you identify them. Your brain identifies them. And you quite frequently can't distinguish them. And the reason is because there's notes octave apart in everything that you hear, even a single pitch. I'll explain that in a few minutes. But here's a graphic example of octave equivalence. What you're going to hear is an organ playing up the chromatic scale. And it just keeps going upward, and the pitch never gets high. It goes up forever, and it never gets high. And see, that can go on in perpetuity. It's going up, but it doesn't get high. So what's going on there? Yes?
They're fading in lower octaves very
Right.
brightly.
You're hearing a pitch, but you're actually hearing a sequence of octaves. And so as you go up, an octave up here fades out where another one comes in. If you listen carefully to that example, you can hear that happen. So you have this snake-like effect of this disappearing and this fading in. So you don't hear that unless you listen for it. You listen closely, you can tell it. But basically, your ear doesn't mind because you make the octave identification. You're identifying those octaves as the same note. Musical notation does that. We say E flat. What does E flat mean? Is that a single note? Well, no, that's what mathematicians would call an equivalence class of notes. You're declaring all notes the same if the interval between them is an octave or a multi-octave. So, hit E flat on the piano, well, it's that one, it's that one, it's that one. In principle, it goes up infinitely far and goes down infinitely far. So, it's an equivalence class. And that's because our brains identify the octave. And so music makes that identification. Okay. Now, I'm not going to bore you too much with this. It would really ruin your night. But the additive version is measured by the real numbers with the operation of plus. That's like adding semitones. Yes.
If our brain didn't do that, it would be different, wouldn't it?
If your brain didn't get octave identification,
It would all be totally different.
but you see, your brain is thinking the number 2. Your brain just
So it all
likes
just
2.
depends on
But
this
if your brain didn't do that, you'd have a universe where there wasn't the concept of 2. Now imagine a universe where you didn't have the concept of 2.
And everybody's brain does the same thing. There's 6 billion people.
I'm telling you, it's a
Brain,
basic, 2 is a basic concept. It comes up in rhythm, it comes up in the horizontal, the vertical
The
structure.
dogs and cats and snakes and things,
Sure,
they all do too.
they like 2.
Western wives think in terms of twos as well. It's a bit of a problem. Johnny.
We could have a long discussion about that if you want. Now, I don't want to, when you go up to thinking in terms of ratio measurement, now you're talking about positive integers, and now you're multiplying. So here's all integers and adding. Here's positive integers and multiplying. This is measuring intervals, say, in semitones. This is measuring intervals by ratio. The mathematical connector is the log and the exponential. I'm going to convert 12 semitones into ratio. I take this formula and replace the x by 12. What do I get? 2 to the power 12 over 12, which is 2, to the power 1, which is 2. And that basically says 12 semitones is 2 octaves when you make the translation. Okay? All right. I go the other way, and I take 2 octaves and I plug in here. So I'm taking log base 2 of 2. Now all you math people will tell me that log base 2 of 2 is what? It's 1, and I multiply times 12, and I get 12. So 1 octave, which is ratio of 2, translates to 12 semitones. So that just exemplifies these. So 1 is an exponential, 1 is the logarithm. That gets us back and forth between the musician's view of what an interval is and a mathematician or physicist's view of what an interval is. It's the log and the exponential. We also don't have to be stuck with semitones. In fact, microtonal music demands a much finer resolution. So actually, most synthesizers have not only semitones, but what's called cents. That divides the semitone up into 100 equal units. And now, even though that's still discrete, it's not a continuum, it gets us close enough that it doesn't matter anymore. So just for your enjoyment, I'll play you. Here are 2 tones, and the second one is 1 cent higher than the first. Now keep in mind, 100 cents make a semitone or half step. Okay? So 1/100th of a half step. Here are the 2 tones. You could all hear that, right? Okay, here's 10 cents. Now you will begin to hear. You may sense that the second tone is a little higher than the first one. Here's 20 cents. You'll hear it. Okay. That's when your baritone's flat and you do this. I'm trying to elicit. I'm not going to bore you with this because we're about out of time. But basically, the moral of this story is that there are no rational intervals on the keyboard except the octaves and multi-octaves. In other words, 2, the octave, 4, the double octave, 8, the triple octave. Those are the only intervals on the keyboard that are rational, meaning they're the quotient of 2 integers. If you take a tritone, so that's 6 semitones, it's 12 to the power 6 over 12, 2 to the power 6 over 12. 6 over 12 is a half, so it's 2 to the power 1/2. That's the square root of 2. You probably learned somewhere in grade school that square root of 2 is not a rational number. The ancient Greeks knew that, as a matter of fact. So there's all kinds of irrational things on our keyboard. Why do we have them? Well, we have to have them to make equals temperament work. And here's the fact. Once you understand a little bit of mathematics, here it's not deep, but I don't have time for it. It doesn't matter how many equal intervals you divide the octave. You can divide it up into 22 equal intervals. Doesn't matter how many equal intervals you divide it up into. If you have equals temperament, the only rational intervals on the keyboard will be the multi-octaves. That's the only way you can have equal temporal is to have all those irrational elements. All right, now here's another, going back to our modular arithmetic. Here's the circle of fifths. I guess this goes back to Bach. Our progressions in barbershop, a lot of them follow the circle of fifths. So you start with C and you go up a fifth and you're at G, right? Music scholars, you go up a fifth from G and you're at B, and A, blah, blah, blah. You go all the way around and you notice that you've hit every chromatic note. Okay, you've used every note class when you get around there. Now, why does that work?
7 and 12.
7 and 12 are relatively prime. This is 7 semitones, and we're in a system of 12. We're thinking mod 12 because when you count to the 12th count, you're back to 0. So our circle now has 12 units, and we're adding 7s. 7 and another 7 gives you 14, but that's 2. And then 9. 9 and 7 is 16, but that's 4, and blah, blah, blah. Then you see that you have every modular integer, mod 12, in the circle. So the circle of fifths works because 7 and 12 are relatively prime. How many intervals are there that are generating intervals? How many intervals are there which, when iterated, give you every chromatic note before you get back to where you started? Well, you have to start thinking how many numbers are relatively prime to 12. So how many? 7 is 1. 5, that's just going the other way. 5 is going the other direction. 1 and 11. Anything else?
That's it.
I think that's it. So there are 4 generating intervals. One is going 1, that's going up a half step. That obviously gets you everything. 11 is going down a half step. That always, and then there's the 4th and the 5th, and they're kind of reciprocal to each other. So that's why Bach's circle of fifth works. It's all modular arithmetic. This is the integers thought of as ratios now. Now this is a ratio. Okay, so the integer 2, we just said that's the octave. So I start that F right there, and I think what pitch has ratio 2? What would that note be? Twice the frequency is there. 4 times the frequency would be the next octave. 8 would be the next octave. 16 would be the next F up there. But what about all these other integers? Well, that gives you other tones. 3 gives you a note that looks like a fifth from that. It's not the fifth on the piano. This is the real fifth. It's a little different. 4, these intervals are perfect on your piano. The octave, but the fifth isn't. At least you know that's true if what I told you a minute ago was true. There's no rational intervals except the multi-octaves. So this interval here should be 3/2. That's a nice rational interval. Yeah, 3 halves, but you don't get it on the piano. It's something different. This is what looks like it ought to be a major third. It's 5/4. That's the ratio of the major third right there. You know something's screwed up with the scale because that looks like a minor third there and that looks like a minor third. But the difference is, the interval here is 6 to 5, the interval there is 7 to 6. Those are not the same number. So you can see that things are misfiring in a hurry with equally tempered scale. They're rendering all these minor third intervals as exactly the same. Now, you look at that sequence of notes, it greatly resembles the graph of the logarithm. Why so? Well, because of our translation. It is exactly the logarithm function that translates back from thinking of pitch as a ratio to thinking of pitch in terms of semitones. So the graph, that's exactly the graph of logarithms. So. Now, what gives pitch? It's a periodic function. It's something that repeats. It's an oscillation. It goes, this function, if I take it from here to here, and I exert this portion, it looks exactly like that portion. It's a repeating pattern. That's exactly what gives a musical tone to your ear, some oscillation that has a repeating pattern. And the number of oscillations per second is called the frequency. The period is the length of the period, the length of that 1 unit of the repeating pattern. And the frequency would be 1/p. So if the length were a half, okay, then you would have the reciprocal, or 2 beats per second. So the frequency and period are reciprocal to each other. Right? And of course, frequency is measured in hertz. There's our physicist cycles per second. So how many of these go past 2 in a second? Well, that's some frequency. The pitch or the tone that you hear, the pitch will be the number of cycles per second. Now, we know that we can distinguish a lot more about a tone besides its pitch. You can have a trombone and a trumpet playing the same pitch, and your ear can still tell the difference. How can you tell the difference? It's not by pitch. They have the same pitch. There must be some other parameters that allow you to distinguish timbre. Same thing that allows you to distinguish an O vowel from an E vowel. Or my voice singing the same vowel from Bob's voice, even though it would be similar, it would be exactly the same. You can tell us apart. What distinguishes? Well, let's go back to something more basic. Here's the most basic periodic function. You encountered it somewhere in the 6th or 7th grade, I hope. Y equals sine of x. If I just take the most simple oscillation possible, let's say a weight dangling on a spring, I pull the weight down, and it just has this simple motion, release it. Now if I put a pencil on it, and take a piece of paper and go like that across it, it draws that shape right there. That's the simplest kind of shape you can have, simple periodic motion. It has a sound. If I can speed it up to where it's in the audible range, it sounds like a dull hum. There it is. That's a sine wave. It's the most uninteresting sound you could have. It's nondescript hum. Now here's the amazing thing. That dull hum, or that sine wave, is the basic building blocks. All musical tones are built out of that one in a way that I probably don't have time to do this. Okay. Now, if you have any old periodic function, like that one you just saw the graph of, something like that, mathematicians have long known, due to the work of a mathematician named Fourier, that you can write it as an infinite sum. That sigma is a summation. And when it says k equals 1 to infinity, it means you put in k equals 1, now put in k equals 2 and add that, now put in k equals 3 and add that on, keep on going to infinity, and you add up all those functions, you get the one you started with. You notice that this just has sines and cosines in it, but cosine, the graph looks just like sine. It's just shifted over. Now, math also says a way you can recover those coefficients. This is some calculus, won't ruin your day, but you can do it. If you're first semester calculus, you understand what all this means. It's just computing those things using some integrals. You can mess around with that formula and get it to not involve the cosine. It's just the sine, and now you have a coefficient in front of each. Now these are called harmonics. These summands are called harmonics. Each one has a weight. That D out front says how heavy the thing is. So if D is a little bitty number, there's not much of that thing there. If it's a big number, there's a lot of it. The K goes in front, that's the frequency right there. If K is 2, that doubles the frequency. If K is 3, that triples the frequency. K is 4, it quadruples the frequency. So you have that sequence of pitches that we just described a minute ago on the staff. And the final one, beta here, that's nothing other than a phase shift. That scoots it over left or right. All right? So it's not so important. So there's really two important parameters, that weight, and of course that thing that says which harmonic it is. And now, you can isolate those, and you've probably heard singers that can do things like this. When you sing, everybody's doing it, he's singing that pitch, but you hear all those other things. You hear the high pitches, it's right there, but you hear that other stuff. So what's he doing? He's moving around these weights so that if you move one up a lot, you hear it as a pitch. Those are just the harmonics. All the singer is doing is singing a single pitch, so that frequency never changes, but he's moving his mouth around so that certain harmonics get amplified, and you begin to hear his pitches. All right. So these again are the sequence of harmonics that appear in the harmonic. All of those notes are in every single pitch you hear. Now, let me move out of this and give you another quick demonstration that I think you'll enjoy, and then we'll be out of here and it'll be beer time. Now this is a great little app. What you see there, here's a periodic function. That red line, no actually it should be white, but there's red stuff there too. That white line is what we call the sawtooth wave. It's got a very buzzy sound. I can play it for you. Hope this isn't too loud. It probably will be. I'll turn it down. Don't drive crazy. That's the sound of the Now, as a matter of fact, what these things represent is the harmonics. That's the first harmonic and its weight. The fundamental pitch, which was right there, that's the second harmonic, which is an octave above it. So that's right there. And that's the third harmonic, which is an octave and a fifth. So that's right there. And then 2 octaves above, which I'm not going to try to sing. And then 2 octaves and a major third, 2 octaves and a fifth. That same sequence of pitches that we just experienced. Those are all in that sound, every single one of them. And it's the relative weights of those that allow you to say, well, that's a sawtooth wave and not a trombone. So I can vary the texture of those by moving those weights. Now, if you want to see and hear those being added on one at a time, let me start the sound. And I'm going to remove those harmonics by sliding this. And you'll hear the sound change. And we end up with a simple sine wave. That's the fundamental pitch. And you can see it there. And this thing indicates the weight of that. Now, if I start going up, what it's doing there is this is a remarkable theorem of mathematics. With a single sine wave, that's as close as you can come to approximating that sawtooth. Now it's going to add in the sine wave of double. See that yellow line? It's twice the frequency. So if I bring that over, I'm going to add in, it'll be a tone that's an octave above. Yeah, it's hard to get a cursor to stop there. Let me go and stop the first 3. So that's, and then a fifth above that. Okay? You may be able to hear those pitches. And if I keep adding, after a while, it doesn't matter much up here. Why? Because you're out of your audible range, and you don't care. So that's why that infinite sum might as well be a finite sum as far as our hearing is concerned, because we only hear finite range sumbands anyway. Okay. Now, can you actually hear them as pitches? We start up again, and I claim, all right, that's a fundamental. That's an octave above. Look at that yellow sine wave. It's going twice as fast. Here's an octave and a fifth above. Can you hear that octave and a fifth in there? Well, if you can't, I'm going to turn it up, and you will hear it. Can you hear it now? Now I'm going to fade it back down. Keep track of it. Got it? You can hear it. All right? There's 2 octaves. Here's 2 octaves and a just major third. Can you hear the third? Can you hear it? All right, keep track of it. Don't lose it. There it is. Got it? Now, this is one of the most remarkable things in mathematics. I can take any old periodic function, not just a sawtooth wave. This little app allows me to draw. I'm going to draw just some stupid thing that's crazy. The mouse. And it can be approximated by these harmonics. So there is Math's best attempt to do it with 1 sine wave. There with 2 sine waves, with the first and second harmonics. You notice as I keep adding, see that red curve? See how quickly it converges to the white stupid thing I drew? If I start adding harmonics, it gets closer and closer and closer and closer to what I drew. And I just drew some stupid thing. It doesn't matter what the periodic function is, by choosing the correct weights and the correct phase shift for each harmonic, you approximate it. And the approximation gets good. Now I play it. It's a different fuzzy sound. And again, I make the harmonics go away. Can't isolate the first one. The mouse is just won't do it. There it is.
below the line, are they divisions?
These right here?
Yeah, the ones below, no, below the line.
Oh, there's nothing below the line. These are all positive weights.
Phases.
Okay, I'm looking at the thing on the bottom.
These are the phase shifts. So each harmonic has, so there's the first harmonic. It says that's the weight of the first harmonic. Okay, not very heavy.
Right.
This is the phase shift. That means it's shifted to the left, probably.
Okay.
Okay, so it's a sine wave. There's two parameters you have to say. One is its amplitude, like how high and low is it?
One's where it is.
And one is, let's scoot it forward or backwards,
Right.
you know, in its phase. And so by adjusting each harmonic appropriately, you can come up with the right coefficients to approximate any periodic function. And of course, as I said, mathematics tells you a given periodic function how to pick off those coefficients. You have to work some integration problems. You have to do some calculus.
Is that, if you've drawn, when you were drawing,
Yeah.
a peak somewhere to the left, that would just be the phase of that peak? Is that right?
You're talking about the thing that I drew up there on the
Yeah,
top?
when you drew it, and you had a peak somewhere, and that is how far it is from the start, or?
I'm not sure I understand what you're asking. So I'm going to draw just something stupid.
Yeah, you draw something stupid.
Okay.
Hang on.
Let me get rid of the harmonics and draw something stupid. Let me get it down to practically nothing. In fact, let me get nothing at all.
Yeah.
All right. Now I'm going to draw something stupid. So I go up, go way down. I don't care. Over, up, down, and it closes off to a periodic function right there. Now, the Fourier theory is going to do its best to reproduce that. If I say one harmonic with a single sine wave, there's the best. See that red thing?
Yeah.
That's the best it can do with one sine wave whose period is the same as the function that I drew. Now it's going to add in something that makes two humps, two periods. So that's this harmonic number 2. And you'll see it when it adds that in, the approximation gets a little better. See, the red curve approximates the white one a little better. If I go to 3, it gets pretty good. There's 3, 4, not bad. If I add a whole bunch, it very quickly hones right in on the curve. So I don't know if I answered your question. The individual harmonics have different peaks from the peak of the function that I drew. And how to tell in the nth harmonic how it lines up with what, you know,
okay.
what it is. Now you're talking deep stuff.
Yeah.
Yes.
If you, with your squiggly line, drew the right shape and we closed our eyes, would we be able to hear a clarinet or a trombone or a trumpet? Or?
You would, but I warn you this. A lot of your ability to distinguish determines not just the timbre of the tone, it's the attack and release of the tone. So if I took a trombone and I isolated a little passage that didn't include the attack, and if it was perfectly regular, so it has that non-human quality of absolutely sustaining the frequency perfectly, it sounds pretty electronic too. So you would say, ooh, that sounds like another electronic tone.
So that's why it's hard when you have an electric keyboard. It sounds like it's got a dodgy trombone function. That's why.
Because, yeah, that's right. It depends on the attack and release. The little, you know, if you've got a flute, that little puff of air. You know, there's other things that allow you to distinguish the instrument as well as pure timbre.
Is that why piano samples tend to be much better than other instruments? Because you can predict that the piano will decay much more regularly.
Yeah, the piano has a pretty simple attack. Yeah, that can be synthesized. Yeah, that's right. So, yeah. But as far as E's and O's, yeah, you can screw around with the formats of an O vowel, and if you know what you're doing. And you can also do this by adjusting with the mouse those parameters down there. So you don't have to draw the graph. You can just create your own by adjusting the parameters. You know what you're doing, you can make it go, oh. Still sounds electronic, but you can tell it's an O vowel. So, yeah. All the distinguishing of timbre that you do is the relative weights. All of your ability to distinguish timbre is right here. Those numbers, those relative weights, allow you to distinguish everything that we distinguish in terms of timbre, you know, of a sustained tone. Yes. And those are just the overtones. Those are pitches that you can hear if I turn them up enough. And you can hear them, if If you learn what you're listening for, you can almost always hear that first harmonic. It's the one that's an octave above. So if I sing that, listen for that, you can kind of hear it up there. You have to. It's kind of like hearing the overtones is, you know, these things where you say, find the cow in this picture. There's a cow in that picture, and then you stare at, there's his nose, yeah, okay. And then once you see the cow in the picture, you kind of wonder how you ever missed it. Listening for overtones is like that. If you know what you're listening for, you can find it. And once you've honed in on it, yeah, you can hear it pretty well. But you have to know what you're listening for. Okay, questions in wrap up? We may probably need to stop, because it's the end of your day. I know